here essentially is di by dt. And x2 dot here is simply dv by dt. Okay. And I can write these equations in a matrix form, which is 0 minus 1 by L and 1 by L, 1 by RC is equal to or times x1, x2 plus d by L0, 0, 0, V1, V2, which is the same equation written in this form, and then you can have just one this form. Okay, so anyhow, so
what's on the other side there? The last one?
V1, V2.
V1, V2.
Yeah, V1,
Before
V2.
that, in the matrix.
It's D by L, sorry, D by L.
What is small d?
That's the duty cycle. That's the duty cycle. Okay, so we have, now this was one of the first attempts at small signal modeling. So if we could convert these equations into state variables, then we have a chance of understanding the average behavior of the system. We don't.
This state variable, whatever is written, is for on state only.
This actually simplified. It's not really on state because we are considering the average voltage at this point of time, which is dV in. So it's sort of slight extension of the truth.
So when you take off state, your I.
So now
it doesn't match with the instantaneous equation. The instantaneous equation would be di by dt equal to V in minus V naught by T. The instantaneous equation.
yes, it doesn't match. It doesn't match. So there's a trick here, which we have already used. The trick is we use dV in, right? So dV in is actually the average voltage at this point of time, right? So we are taking that voltage to derive these equations. So it is more of already an average model, right, which we are writing in a state variable, state equations. Does that make sense? Okay. So when this was done, let me actually write this down then in can I go ahead and erase this? Yeah. So in more clarity, you had x1 dot is equal to 1 by L no, we'll have to come back to this. Okay. So what it led to was that you can view your inverter as that we have a DC transformer, and then you have an inductor, you have a capacitor, and you have a load. Okay, and this is D, and this is dV in. Okay, this is your V in, and essentially you have, this is called DC transformer. Okay, and the D decides the turns ratio of this transformer. Essentially, the state variable equations led to this conclusion, that if you can write the equations like this, and if you can expand on the state variables, what does that mean? It means you have a system like this. Okay. Now, so now you say, okay, I have actually a system which doesn't have any switching. There is no switching element on in this system, right? So now here, if we do a AC perturbation to our state variables, okay, basically we take our state equations and we say we're going to perturb them. So we're going to perturb them by slight quantity. So perturbation in state variables is something like this: x is equal to x0 plus, you can say, x tilde, u is equal to u0 plus u tilde, and then d is equal to d plus d tilde, where these are all DC values, x0, u0, d, and these are the AC values. Okay. Now, and if you look at here, x is I, so we can say I is equal to IDC plus small perturbation, and your U is V output, which is VDC plus small perturbation. Okay, and then D is your duty cycle, D plus D perturbation. So that's what we have done in our state variable equation, and then you can essentially see how they play out. When you substitute I with IDC plus I tilde. So those equations, there's one error in here. This really should be di by dt, and this should be and this should be di by dt, and this should be dvo by dt, because when you do, IDC term disappears. So this really should be di by dt and dvo by dt. So you should go ahead and make that change on your. Then some of the DC terms fall out, and you're left with only the time varying terms. And this is another state equation which says, let me write down on this side. So we've got so x1 dot, if we have this tilde is equal to 1 by L x2 plus d by L u1 plus d by L u10, and then x2 is 1 by C x 1 minus 1 by RC next to it. So U10 essentially represents your V in perturbation. and then your U1 is, this should be V out, I believe. No, V in. This is V in, not V in. V in. This is V in. So there are two. This should be di by dt. This should be dvo by dt. This should be V in. Okay. And then 1 by C x1. X1 here is I. And then 1 by RC x2. X2 is V out. Right. So x1 is your inductor current. And x2 is your voltage. Okay, so this is a state variable treatment, and however, this approach gave us first insight into average behavioral modeling of converters. However, it was extremely difficult approach because trying to every time you design a power supply and you had to correctly estimate the parasitic components, then you had to rederive all the equations. So it was very complicated, very difficult, and so somehow anyhow, so it was sort of dropped as an approach which can be used by practicing engineers, right? And practicing engineers are not really scientists who would love to derive these equations over and over again. So this approach was abandoned. One of the first attempts, but it is still taught because it was one of the first approaches, but it is abandoned for practical use. So what happened after that? There were several attempts. And one particular attempt actually gave us much simpler model, okay? Much simpler model, which is what we have implemented in our system. And this simpler model essentially says, okay, I want to have a model which is not circuit variant. If my circuit components change, if I have parasitics, that this particular switching element model does not change with circuit elements. So this particular model is actually the point I want to make is it looks very similar to this, okay, to the state variable equations. It looks similar to it, but the good part about it is that it is independent of circuit elements, right? But the basic fundamentals are exactly the same, and let me write the equation for you on that one. So this particular model which we're going to show, we make this have three terminals, A, P, and C. Okay, so this element is defined to have three terminals, A, P, and C. Okay. Now, what is A? Now, since this model will be used in buck boost converters, in boost converters, in other, even in flyback converters, so you say we define A, node A, as something which is not connected to the diode. Okay, which is not connected to the diode. Then you define C as a junction between diode and the power switch. Right, those are the definitions of how to use this switch, right? And you define P as a terminal, a diode terminal not connected to the switch. Diode terminal not connected to the switch, right? So with these definitions of these terminals, right, A, C, and P well defined, you have, we derive at a model which is simpler than SSA. It does not change with circuit or component modifications. And we will identify PWM switch variables. Basically, this approach is very similar. It gives you very similar results. We identify PWM switch variables, average them, and perturb them. Okay, what are the PWM switch variables? And how do we average them? And how do we perturb them? I'm going to show you in a minute. But that is the pulse width switch model, which now you can use in just about any topology, and you can have a Bode plot, and that Bode plot is good. Is pretty good starting point for your power supply design. Okay. Right. So with this model, you can quickly do your power supply design, and you can have a Bode plot, and you can have a compensator, and all the good stuff. So now the details of this model.
This is something like Kopek modeling, sir.
Something like Kopek
Kopek.
modeling. Tell me, what do you mean by that?
Colorado Power Electronics has built-in model for all
Yes.
boost.
Right.
This same kind of model.
It's a similar kind of approach. It's a similar kind of approach, and I think it is slightly different. I think it's slightly different. Let me draw the equations for you. Okay. So what we have in a PSpice domain, what are we looking at? So in a PSpice domain, the way we implement this model is as follows. So we start with terminal A, terminal C, terminal P. Okay? So the three terminals are the starting point. Now we say, okay, I'm going to have a current here, which I call IAT. I'm going to have a current here, which is ICT. And what we do is say IAT is equal to ICT times D. D is the duty cycle. And we say voltage VPC is equal to VAP times the duty cycle. And if I have to we have a G source here, and then we have an E source here, actually I have another terminal in between, which is the E source. Let's call this terminal N, which is the hidden terminal, and then we have got voltage source here, which is 0 volts. Right? So this here, E, essentially is what is the voltage which is function of VAT times D. And this voltage is essentially ICT times D. This is the inner workings of the average switch model. Okay, so we have got this voltage, which is the function of the current in the C terminal times the duty cycle. So you have a duty cycle command, which is coming in from here. And then this voltage here is a function of what's over here. AP times T. Okay. So I'm going to show you how we have implemented in PSpice. So what's important is these three definitions, A, C, and P, and then this implementation. And then you can just simply take your converter and replace your switching element with this element here. Okay, let's see the PSpice part of it. This is your cycle by cycle buck. Okay? So you got the switch, the diode, and then this is your average switch. You basically take out the switch and the diode and replace by this switch, A, C, P, and then you have a variable duty cycle there. And the way this is implemented, so we have a file called average switch, and basically we have, okay, so you have a G source, which is from A to P. The value of this basically is, this is the G source between A and P.